That's right. Yeah, that's right. Particular piece of mouse. This okay, it's lifetime 3. Oh, that is a population. They have a limited lifetime, right? So the determined approximation population after 1 year. Yes, I think that is you have to. This is a discrete. That information is per year, right? 0.6 is a surviving or death rate. One is death rate, another is surviving rate. That's right. Can we? Oh, where is that? Are you looking for something?
Yeah. So S is the survival rate.
It's survival rate. Yes, survival rate.
So here, the 0.6 and 0.4 are the survival rate.
Survival rate. So, what is the first? What does that 3 number of first row? That will work out. That allowed you to work out the next generation, right? Or next year. So yes. I can't remember the detail at the moment. It is just oh, this very special case. It's a lifetime. Oh, so okay, I'm into now. So this special lifespan is just 3 years. So that's why you use 3 by 3, right? The initial female mouse population is given by these matrices. So that is initially, so this is section, and then you have used a matrix to determine what happened next year by multiplication, isn't it? So the matrix is introduced, allowed you to work out what would be the population in next year, in year 1 or year 2, right? So mathematically it's very simple. It's just a matrix product, but this application has been used to study this the change due to, you know, there's certainly why there's 0.4. Can you tell me?
0.4 is the survival rate.
What you can do, yes. Can we just write it down? So oh, can't see it. So basically, it's just this is matrix is invented by this Naismith, and so that people can use this matrix to by using multiplication of 2 matrices, then they can predict what will, or it is predict. They can predict what will be the population next year. So obviously these can we start from initial conditions 16, 25, 14. What are they? Initial female mouse population given matrices. How can they have 3 numbers? That is year 1, year 2, year 7. Is that right?
I think it's 1-year-olds, 2-year-olds, 3-year-olds.
That's right. You have defined that one first. Now, can we just go to the whiteboard? I show you. This is just a simplified multiplication rate equation. Okay. So if you use a matrix, I show you how to do to learn this one. It's just use multiplication first. Can you see? Can you? This is matrices, right? What is the first year's column matrix? Do you remember? 16. Or what can we write this 3 number there? Can you write this 3 number here? I show you. This is just simplified the rate equation. Okay, so this is compact. I could say compact rate equation. Rate is the growth rate and survival rate. rate equation. So that is in the that can be, this is in the single matrix form. Oh, just one, right? One moment. So no, I'm trying to show you is this one. Can we put this 3 number here? Can we call this A, B, C, and R1, R2, 0, 0? Can we use this abstraction? And without this number, okay? And this is the 3 numbers. Can we use the N1, N2, N3? Okay. So what you can do, can you first expand that by a matrix product row, multiplication row? Can you expand this? Then we can read the meaning. One moment. We still should get the matrix, a single column matrix, right?
Oh, yeah.
Yeah, we still got a single, this is called a single columns, single columns matrices. But actually, we know these matrices is actually equivalent to the vector notation. Vector. That's right. It's 3. Can we simplify this? Can we simplify that? So this is first year. Do you mean this first year? Year 1 is year 2. Is that right?
Yeah.
Okay. What are they? Can we just write down here? This you cannot simplify the first one. You got A N1 plus B N2 plus C N3. Right. Now the second term is simple, is R1 N1. So R1 and R2 are 2 rate. Now by definition, what is the definition? Which is survival rate? R1 are in this general definition here. So both are survival rate, right?
R1 is survival rate for 1-year-olds.
Okay, surviving rate. Okay, so survival rate for 1 year old. Okay, so this is a so after 1 year they grow up. So that is why so this is come from the, where does this what I forgot, what are these ABC mean? ABC is 3 number. Now can we can we just rewrite this one, because this is very compact form. So basically in year 2, this is how can we define this year 2? I'm trying to generate this formula as a rewrite this formula as a simply the linear equation. So what do we call this one? These 3 numbers. Let's just denote this properly. It's because this mathematics is accumulated by many years, so there are many applications. This application is can we just rewrite this one so that we don't have invoke this subscript? And we have to make sure that is can be rewritten the equation for 1 year old. Okay, so 1 year old. But this survival ratio for 2-year-old, right? And 3 years, not have the 3 years. They only can live for 3 years, right? They die. So that's for surviving is 0. 2-year-old. Yeah. Okay. Now, how can we choose this one? Can we set can we use PQR? PQR. I just trying to not exhausting that subscript. So this is year one. Can you see PQR? And that matrices, there will be PQR, PQR subscript 2. Can you see? I'm trying to figure out the, see, go on.
A, B, and C are reproducive rates for each year.
Ah, yes. So they have baby, right? So have baby. Each of them is capable can have baby because are female. Well, that is another assumption. Yeah, that is a birth rate. Is this birth rate?
Yeah, for each.
Yes, it's birth rate. It's a birth rate. You know what? People trying to use matrix birth, not birth. Birth rate. Birth rate. Okay. So in other words, the added one, you see, the added one. Oh, okay. That makes sense now. So obviously this for this rate for different age group. Can you see? Let's just rewrite this number. So you can see how I recall this this piece of knowledge. I haven't touched that for a while. Can you see? And so I will try to write the equation for you very soon. So that is a birth rate. Can you see? Birth rate for can we just, they're all birth rate at different age, right? Birth 1, 2, 3. All right. Not bad. 1, 2, 3 because the last B must be 0, right? Anyway, we use this note here, and B for birth, R for surviving. Now let's just rewrite this equation. Okay, so we got to write this linear equation now. P2 is equal to, according to our notation, that should be PQR 111. I have to rewrite this. Sorry, I have to take some time. This is not. Yeah, it will make sense that way. I just reconstruct. I'm trying to reconstruct the birth rate equation. Wait a moment. So that is a B1, B1, B2, B3. So according to this one, we can reconstruct this relation now. So basically that is a B1, population 2 is a B1. 1 year old B1, P1. That makes sense now. P2, P1 plus B3, Q3, PQR. Sorry, PQR. PQ plus B R1 S3 read PQR. Sorry. PQR1, okay. And another that's another one is a PQR. I've done here. PQR in year 2 is equal to, and in this case, how can we find the Q? Q is in this case, depending how can they survive, right? For the first one, for the first year, they can survive, right? So that's why we can write R1. What did I do that here? I changed my notation. R1 P1, so the R1 P1, all right. And the second is the last one. This is R2. R2, R2Q. All right, so this is a simultaneous equation, can you see? So for some reason, so basically the P2 next year, P2 will increase. This is called age group, can you see? That different age group. So the first age group, and they will have baby, can you see? And because each age group is generated to give birth to the baby at a different rate, can you see? That rate that would be the sum of the age group 1. Can you see? That you can call the 1 years old, 2 year old, and 3 years old. Can you see? But for the second age group, the contribution, why the contribution only come from P? That is something I forgot. Why is it this age group only? Oh, this is surviving. Oh yes, each year they have struggled to survive. Do you agree? So therefore, some animal will die. Do you agree?
Yeah.
So therefore,
3-year-olds will die.
Yeah, 3-year-olds will die because too old. Okay. But my question is, why did the owner consider the P1, the first age group?
R2 is also survival rate.
Yeah, R2 is survival rate, but their contribution is different. Can you see? If that is a age group 2 or 2 years old animal, and how can they just work out from one single term? That's my question. Can you see? In this age group, only both year 1 and year 2 can survive. Do you agree?
Yeah.
Now, so what is original? What is should we plus this Q1 as well? I put a question mark here. Why did the owner consider these surviving from age 1 to age 2?
I think the 2 to 3s also survive.
See, that is, we are based on this product. Can you see these 3 simultaneous equation is based on our matrix production. Can you see we expanded that because yeah, go on.
These are 2-year-olds they were 2-year-olds.
They were 2 years the previous year, right? They survived. Okay. Now so they're still there. So basically we have to ask, what are these 3 numbers? Are these number
original population?
Original number of 1 years old? Okay. Can you say year 1? This number of year 2, is that right?
Oh no, this is 16 equals 1 year old.
Yes. That's the number of them, okay? That's why I use this year's number. Can we, this means number as notation for number. That means for number. Okay, this number. Okay, how about this 14? 14 has already reached to year 9, year 3 now. Can you see?
Yeah, but they can reproduce.
They can produce. That's why that is contribution. Like in the contribution for year 1 next year, they can produce at that rate. Yes, but my question is, what happened to year 2? Year 2 will be made by. Oh, that makes sense. Year 2 will make by people survive from the year 1 to year 2, right? So therefore, there's only one term. Okay, that makes sense now. So this shouldn't be here. So this should be here. So this term should be here. And you have the question is, how can we just put Aha, you edit the term. Did you edit the term?
No, you just keep.
Oh, I haven't cleared that yet. Yeah, this application very you have to use this very often. But I am more familiar with Markov. Markov is matrix is also used to predict say weather or forecast. Next chapter you will talk about the Markov, but let's just continue. So now we know this Q2 is a population of year 2 in the second year, right? And obviously because they grew and survived, so that will depend on the first group. That makes sense, okay? That makes sense. Yeah. And the third group, the year 2, year 3 animal will be those in year 2 who can survive at this R rate, R2 rate, can you see? And that's all. So there's no, that's all, yes. Oh, that makes sense now. Can you see that? So why did I spend this time to reconstruct this? Because matrix is very compact form, right? And which allowed you to write a lot of the rate equation, simultaneous equation. Can you see? So this is actually simultaneous equation, isn't it? This is a simultaneous equation, right? So if I put them together, so if I just perhaps I use I can use this part. I can generate into a more. I can rewrite this into more general form. I'll show you. Okay. So what I can do is to rewrite this question into the more general form. This time, I put this. I put the right-hand side on the left-hand side. You can see, and this time I would prefer to this. Instead of use this PQR, I can also use XYZ. Doesn't matter. I still use PQR. All right, use PQR. So basically, you got this in this term. So we can write down here. So that's B1. So B1, P1 plus B2, Q1. So that is all determined by birth rate, okay? Because every year, each group will give the birth at different rate. And that is R1. And then I write this on this side. That gives you P1, P2. And the second one, I just put them, I put the rest of 0. So this is R1. So this R1, so R1. And P1. To make it complete, I just put a 0 here. Can you see? I put Q0, Q1 plus 0, R1. Can you see? That will give you Q2. Can you see? The third one will be this. I put a 0 with a 0 for P1, and that's. I just trying to reconstruct the listening matrix in this way. Q1 plus this 0 R1 or equal to Q PQR, sorry, PQR, okay? So that is a 3 simultaneous equation, all right? Now, you can generate this equation by rewrite this sub-index in this way. So this is, can we call this N? You see, in a year. So that would be N plus 1. Can you see? N plus 2, N plus 1, N plus 1, N plus 1. Hang on, no, not consistent. Wait, I'm doing what I'm doing. Oh yes, I'm right. So I did. Let's write it all over again. that would be P n plus 1. You see, I'm trying to generalize this formula. Q, PQR, PQR, n plus 1, n plus 1. And this is also the n. This is n. Just by generalize this one, because n, 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 n. Can you see that?
Mm-hmm.
So that is a more generous form. Can you see? And if you, this is step 1, step 2, they just to, how do we reconstruct this listening matrix? We just go to next page. If I can remember everything, we can use, we can say B1, B2, B3, R1, 0, 0, R2, 0, 0. That is a coefficient, can you see? This coefficient matrix. That was a P, Q, R. Okay, that is N, N, N. By this product, then that's how we construct this listening matrix. You see, that will become N plus 1. So you can start from any year. I mean, you can from 2020, okay, or you can from 2021. You can start from any year, all right. So n could be any of these. You can start from any year. N plus 1. Sorry, PQ. PQR. That is n plus 1 and n plus 1. So that is how to introduce this listening matrix, or if necessary, if we can denote this as n, then it can use vector n. That is a population n. That is in more compact form. That's n plus 1. And we just introduce L. So this is L. This is this listening matrix. Can you see?
Yeah.
So in doing so, I have first of all reconstruct the simultaneous equation. Can you see? I first use a product matrix multiplication rule, reproduce this simultaneous equation. Can you see? And then generalize that into the matrix form. And eventually eventually we can obtain this even more abstract form of this, you can see the modeling. Any question?
No, I get it.
So you can go even more abstract form. So you can see that basically, forget about this the particular application. I think if you just go to so you can consider this is a 3x3 matrix form. So basically you have this this is more abstract one. So you have this, for example, you got one, and let's draw some coordinate. Can you see? You draw three-dimensional coordinate. It is 3D coordinate. So in this case, you can consider the metric vectors. Can you see? Population vectors. For example, this is one vector, okay, and this is next year's one. So there's another vector. You see. And that their projection. So their projection is this I can use this is a P, Q, and R. That is their projection or axis. You see. So this vector, can you see? Do you remember when you see there's a single column matrix that represents the vector? So in this case, vector is population. Population cannot be a vector, but if you want to talk about more than one age group, then that you can still call it a vector. Can you see?
Yeah.
So, and then how can we predict that the population vector in next year, n+1, we just use a multiplication. Mathematically, which means it's a transformation, can you see? Can you follow me? So air you can consider as a transformation, a 3D, just a transformation. It's equivalent to the transformation, mathematical transformation. Mathematical transformation. Yeah. Last time we were talking about transformer, right? Today we are talking about the mathematical transformation. And this transformation involve number one is rotation, all right? One is rotation, is combination, rotation. Rotation. That's a little bit, which are trying to abstract this idea, see? Another is dilation, can you see? Dilation, time dilation. So in these transformations, if that is R, this is called dilation. So therefore, this transformation can be written as a linear combination of rotation plus dilation. Can you follow me? So that is a more general form. Although if you return to this particular form, that's why I forgot this detail. If you return to this particular form in numbers, right? And you saw, well, at the beginning, probably you saw these were magic, okay? How could they just write in the matrix, 3 by 3 matrix, to get to determine or to forecast the population of different age group? Now it's become clear, right? So today is that I forgot, okay? But I can reconstruct that idea and then regenerate this idea. So that is listening metrics become clear. So this is I think is a very clever application of metrics, because they use, can you see this idea on this page can be used to in other, even spatial relativity, right? When we studied relativity, we have, do you remember we mentioned the Lorentz transformation, right? So that mathematically they are equivalent. So we actually are looking for the vector based on the previous vector, or based on another vector, which can be transformed into this unknown vector. Of course, in the context of population study of animal, then this, you can see this is a population prediction model. Okay.
You also mentioned, I think, matrices before about games. Could we go over that as well? Because I don't remember
what do you mean game? The game?
Like dominance matrix.
Dominant? No, I didn't mention. I mean the Markov.
Yeah, I think it's one where you can find out who's going to win in a round of games.
Yes, that's right. You are talking about dominant matrix, right? Yes. And again, I have to look at your original form. I know this. There are 3 actually. Normally, some people in old days in Math C they only teach 2, but now this teach 3 now. Okay, let's just let's have a look. Yeah, dominant matrix is a matrix to use to predict the winner, I think. So I mix them up. I thought they are. Yeah. But ultimately, you will use our general form. Can you see? The matrix looks different now. Oh, that's right. I saw that one. So 1 is a win, right? 1 means a success, right? 0 means fail or lockdown, right?
Yeah.
So this is very useful. You can use this metrics to make the time for the championship, right? What is it? Australia Open? What's that type called a snap? What is a ground snap, right?
Yeah.
Yeah. So that is you have to keep winning until the last final, right? You can get you can gain the goal. But otherwise you can if you lost, then it's out. So basically, can we read this description here? Here is is slightly different from matrix from listening matrix. So basically, they are looking for the product of two 4x4 matrices, right? In the listening, we just use the 3x3 multiply a single column or vectors, right?
Yeah.
In this case, obviously, they just use the they just use the power. Can you see that is application of matrix power? Can you see? I see. Yes. Okay. So basically, in this case, is P1 relevant in this question? P1, A, B, C, D are 4 groups, right?
Yeah, I don't think it is.
Where is the starting point? Can we just go from start? Where? Yeah, dominant. Yeah, that's true. So dominant matrix can be written in this form. That's very symmetrical, right? Then all of diagonal elements are zero. Okay. So and then they introduce them eventually they use a power vector. Can you see? The power vector. From this matrix, a power vector can be calculated by adding together all the elements in each row. This just a sum, okay? So this, you can see these are the rows. So basically, we use this dominance matrix so that we can, if you found the sum of each row, then we will work out the winner, the score, right? Can we say that score, right? You can work out the score. A, B, C, D have different score, right?
Yeah.
But now you have to understand this dominance metric. You have to really understand the definition and why this number are written this way. And similarly, you can expand that, right? You can expand in that. To see what would be the scenario in the second term. So dominance matrix example computation is shown. Okay, the first we know now we can build the power vector by work out the sum of each row. Okay, can we scroll down a little bit? Okay, now you can in addition we can use a product of two dominance matrix to work out a new matrix. But what does that mean? What does that product mean? You can see that that is second round. You see, in the game you have first round, second round, right? Like a debate, you have debate, right? So in this case, you see the distribution change. A score will be 3. Can you see? B score is 2, and the C score remains 1. Can you see? So that is there's assumption here that there's assumption here that during this game that is a scenario. The outcome, so should I say, the outcome of each round will be determined by a single dominance matrix. If you want to predict what's going on after several rounds, then you can use modification, right? Now, what would happen if they continue? Do we finally get the result? Can we go say into power of the 5 or 6? Can we go that far? Oh, there's another destination. Highest dominance ranking. They have another row here. How do they work out the ranking? This is ranking, and they have to use a p plus 0.5. This is something that's additional row. P1, P2, that is P1 is the result of the first round, right? And the second round, you have to use weight. This 0.5 is you can see the probability. I call it the weight, the statistical rate, divided by 2, and it is a score of 0.2. And this form, the second, these are represent the same, but in the matrix form. Okay.
Mm-hmm.
And what is, so eventually you got the sum. So that is how you work out the score of each team. I think this is similar to the previous listening matrix. At in this one, in dominance one, they're trying to use the language or the form of matrix to represent several linear equations. All right.
Mm-hmm.
So is that the end of definition? Can we go up?
Yeah.
So can we just read this? Can we see this summary here? The first order power, yeah, P1 can be calculated by adding up the elements of each row of M. Yes, we can follow that. The second order power, Vp2, can be calculated by adding the row of M squared. Yes, I can. The overall power vector, which can be calculated by P1, P2. So you can edit more. Can you see?
Mm-hmm.
Because every time you just you just use the previous two power vector with a weight with half with a factor 0.5 for the second P, namely P2, right?
Mm-hmm.
After applying the scalar multiplier to give the weighting, this is called the weighting to each power vector if appropriate. The team or player with the highest value P, that is the rank or score, right? Is said to be dominant team or player. So that is eventually we'll compare with this the number. We compare to this number, which can be worked out by either use a square or product of dominance matrix, or by adding them up in order to add some weight factors, weighting factor, weighting factor, weighting factor, called weighting factor. So another weighting factor, can you see?
Mm-hmm.
Okay, let's just, can we go scroll up to see the structure of this matrix? So can we just no, can we scroll up, return to that one? I will copy that one to this one because I cannot participate at the moment. Can I participate? I can't participate. So remember this form, that is 0.110, and there's one shift 1 and 001 and 100. So yes, okay. If I forgot, you tell me. Let's go to whiteboard. Let's reconstruct this original dominance matrix. Yeah. So basically, what this application about is that they can use a matrix to denote more than one linear equation. Well, these equations are coupled equations. So basically, so what is n dominant is called, did you use M for dominant matrix? Yeah. Just use M. So it's 4 by 4. Can you tell me all of them? 0, 1, 1, 0, right?
Mm-hmm.
And the shift 1, 1, 1. And what are the next?
0, 0, 0, 1.
0, 1 is that shifted.
And 1, 0, 0, 0.
Yes. There are some pattern here. Can you see? This pattern, can you see if I just draw some pattern here? And that's something interesting. I just remind you. Can you see? It's a pattern. Can you see? Pattern here. And this is it's a different color. Can you see the pattern here? And eventually there's a pattern over here. Okay. So they use this matrix, dominance matrix in two forms. One is to generate, one is to find the n, one is to obtain the P1, right? Now how? This first one, then they jump to the M2, can you see? M squared, right? So, and well, we don't have to calculate that. If you quickly, can you calculate that? Can you tell me the result of this M squared? If you just follow, if you have time, you can work out by yourself. Can we just write the result? What would be the? Can you feel this? Can you build this M2 matrix, please? They were find the sum of the sum. Yeah. Okay, thank you. I will highlight this one. Probably more important is to work out the sum of each row. Can you see that we can, if we have chance, we can generate this. We could generate this idea. And that is 3. Sorry, not finally. It's blue. Oh. Okay, the idea is that we generate that in order to generate P, right? So basically sigma is a notation. So this P vector, right? P will equal to, did they use vector? They use a vector, right? So that will be, if I just use the notation of the matrix, that would be equal to M matrix. That is they just column 1, right? Sorry, row 1. So that is I. So I from 1 to 4. You see, and that is just 1. Okay. I just trying to generate this idea. So this is a second one. So that's they use word, but I prefer to use this mathematical form. That is I. That is 2. I just simplify this. I is 3, and I 4. You see, so it's a sum. Okay, it's just that's formation. So that's P1. All right. And from this one, they can work out the P2. Is that right? And P2. So this one, do I have to consider other? So this is a summation of this, or this M square. See M square, how do M square? M square. M square. I don't want to make too. I hate to use numbers because I'm looking for the pattern. So give me some time. M, can we just call M? Can M? Yeah, I don't want to use too many notations. So this is I just said M square I1 M square I2 sigma M square I3 and M square. Just the same thing, the sum of this matrix. Okay, they have two matrices. One is M and M square, and that is Mi and 4. Okay. The reason I do that is because I can generalize this. So can you see? I can generate this as N. Can you see? Can you see that? So therefore, the P, of course, we are interested to find the general formula. So there's a Pn of N round. Then we got this form. You see, just build up this sigma is m to the power of n as I1. Can you see when you study math, this is how to looking for the pattern. Okay. That's a pattern. That's in math. Specialist math is a good example to looking for pattern. Now, what can we do with this MP1, P2? Then we have to use their notation. So the stage 2. So by combining them two, we can work out the total score, right? Consider all of them. Total score will be equal to that is n. We're equal to they got a coefficient here. Can you see? They have a weighting coefficient. Can you call the CK? That's a PK, and the K from 1 to N. Do you agree? And from what they know, we know that the CK1 is equal to 1, all right? CK2 is half, right?
Yeah.
And they didn't they stopped discussing, but maybe if we want to generate that, if that is can be written as a half, can you see? I just guess this just for fun, all right? C3 were equal to the according to this notion, which is this is just power square. Can you see? I guess, all right. Maybe it is not correct, but I just guess that's probably the reason for that. And because the next rank is less important, second rank is less important. So if you want to interpret that literally, right? So that would be, can we generate the formula? What is index? Can you generate? So that can you work out this general formula here? So this is can be written as 1/0. Can you see? So what is index? Should I put here? Yep, that's right. Okay. Although can you see? Although your textbook didn't say, but that would be the rank number. So that be the rank. Okay, the abstract one is called rank. You see. Of course, the higher the better. Okay, the higher the better. So if you come up with a different rank and the 14, A, B, C, in A, B, C, D, and eventually you will get this rank, and just use this histogram statistic. Yeah, use this histogram. So that's one. The distribution. Can you see? Because it could be one of them is the winner. Okay, presumably in this case is D. Can you follow me? This is just I merely use this matrix form to interpret their meaning. So no matter, so this page show you that no matter how many rounds they have in order to find the final winner, you can still use the formula, right? Okay, let's again, can we return to their textbook, how far they go? They probably just focus on second round and they didn't continue to talk. Can you have a look at your textbook?
Closed it.
Matrix. Okay, so what any other example they have come up with? This Lee.
Oh, that's Leslie. Yeah.
Okay. Oh, they have 5 groups. So the number of teams is also can be on any number of teams. So here they got 1, 2, 3, 4, 5. The 5 teams, right? 5 teams. So they use this the build this matrix, and then use you work out the P1 and P2. Or they only end up with P1, the sum of P1 to P2, right? Did they go further? No, they didn't. They think they were just 2 seconds.
It just depends on how many.
Yeah, can we just cool down to see if if they consider the higher order, a higher power like MQ or M4, M2 power 4? Did they consider that formula? They didn't.
No, they just go into Leslie.
Yeah. It's confined to the M square, right? They only confined to M square. Does that? Can we say this competition only involved 2 rounds? Is that correct?
Yeah.
Right. How could they make sure that oh, this is extra question for I ask you, how could they work out that the winner just by 2 rounds, given they have no more than 4 teams, right? Sometimes they're dealing with 4 teams. Are you sure this is okay? I realize now. By the time they interest the team, the matrix, the dominance matrix change. Can you see? They got additional. Can you see? This is a 2, 1, 1, 0, 0, 2, right? They don't. Oh, sorry. This matrix is square. Can we go up, scroll up to see the original M in this example? This dominance matrix. Now down a little bit to see how did they define? Can we go down a little bit? Yeah, that's right. Yeah. Okay. Yes, that's the form is still the same. Okay. Oh, slightly different. Can you see? The dominance, the constructed the dominance matrix from the given information. Oh, okay. I understand now. The dominance matrix is not unique. You have to follow the information about a particular game to build that dominance matrix, right? So what is information? So can we just look at the example? Dominance matrix 5 teams complete a local volleyball championship after play each other once. They all print once. Their results are summarized in the following table. So what is the L? What is W? What is the L? Winner and
L
loser.
is root of win.
Winner and loser.
And W
right?
is win.
Yeah. So that is very specific, right? There's oh, okay. I understand now. This is a very much this dominance matrix is case dependent, right? Because they can based on the first round to predict the second round. That's it. You agree? Because without that information from the first round, we cannot write a number for the element for the matrix dominance matrix. Do you agree?
Yeah.
So that information must be used in order to build M in the first place. After that, you just use M squared and found their corresponding sum of the row, right? In order to work out the score, the final rank. Make sense now? So in so this dominance matrix is different from the first one, 4x4. Do you agree? Why is different? Because they got the outcome from the game, from the competition already. You see.
Yeah.
So basically, they know relatively and which team is relatively stronger than other. So that information has been used. But I can this is simplified scenario, right? It would be interesting if you could find example to show that these two matrices methods fail. Okay. It's another way to study something new is to find their limitation. Okay.
Yeah.
Okay, probably next time we can talk about other metrics like Markov, right?
Yeah.
Okay, I will stop here now. See you next time.
Okay, I'll see you next week.
Okay.
Thank you.
You're welcome. Goodbye.
Bye.